Well, look, we have this Benacerraf problem. We have Wigner's, unreasonable effectiveness of mathematics. We got Platonism. It doesn't seem like a far jump to say, well, maybe an inference to the best explanation is that there's a God who designed the world. Mathematics, maybe be going for divine conceptualism regarding mathematics. God designed the universe, and then designed us to think that way. And what do you make of that? Hey, welcome back to another episode of Parker's Pensées. I'm your host, Parker Case, and this is a podcast where we explore all the deepest questions in philosophy, theology, nature, and life. I really love thinking about cool stuff, so come think with me. Uh, as you'll know, if you've seen this podcast before, I love having experts on to help me think about tough stuff. So today, I have with me Dr. Mark Colyvan, and we're going to be talking about some of the themes in his book, An Introduction to Philosophy of Mathematics. Man, I'm having a hard time right now. I'm really excited about this because I really love the idea of mathematics. I was never very good at it. I didn't really apply myself well. And so I love the idea of it, and I love thinking through the philosophy of it, but I'm not very good at it. So hopefully Dr. Colyvan can help remedy the situation for me. Before we jump in, I want to thank everyone over on Patreon for making this podcast happen. If you've benefited from this podcast, please consider becoming a Patreon patron. You can support the show at a bunch of different levels of support, and there's all sorts of benefits that you get at different levels. So go check the link in the description wherever you're listening to this podcast at, and you can see all sorts of different benefits and ways to support the show. Another way is if you're listening on Apple Podcasts, you can leave me a 5-star review and a comment. That helps the algorithms, helps it get back out there again. And I want to respect my guests. I want to get their stuff out there even more. I think that this is eminently important, and so I want to get as big of a platform for my guest's sake as possible. So please share, comment, all that good stuff. Awesome. Well, without further ado, let's jump into the philosophy of mathematics with Dr. Mark Colyvan. Dr. Colyvan, thanks so much for coming on the podcast.
Thanks for having me, Parker. Great to be here.
Yeah, and so we've had to do some coordination here because you're a professor of philosophy at the University of Sydney. So it's like 9 a.m. for you right now?
That's right. Yeah.
That's great. It's like 5 p.m. here for me. The day before.
Too early to be doing philosophy, some would say, but let's try.
That's awesome. Well, Dr. Colyvan, before we jump in, I just wanted to get some of your story. How did you get into philosophy in the first place?
I started out in mathematics, did a Bachelor of Science in pure mathematics, did a little bit of philosophy on the side, and one thing led to another, and I turned to the dark side and ended up doing a PhD in philosophy, particularly because I was interested in the more philosophical questions in mathematics, like what constitutes a proof, what kind of logic should be using in mathematics. And I found that while mathematicians didn't ignore these questions, they're sort of part of a mathematical practice, the reflection upon those sorts of questions, which most interested me, led me, small step by small step into philosophy. And when it came to graduate school, I was torn between going on mathematics and doing philosophy, and eventually the tug of philosophy won over.
That's fantastic. Was there a central problem in mathematics that kind of drew you into considering it philosophically, or the meta level or something like that?
Well, number of things, actually. I mean, one was just the age-old chestnut of the realism issue in mathematics, whether what's mathematics about, It's one of those very simple to state questions. Physics is about fundamental particles, biology is about living organisms, geology is about the history of the crust of the earth, or however you want to describe that. Mathematics is about ... fill in the dots there, and it's extraordinarily difficult to do that. And so the natural realist position, which is it's about these mathematical objects, and mathematicians are on a voyage of discovery to find out more about them. The alternative is, no, it's some kind of construction, and mathematicians are kind of more like, authors writing a novel, a multi-author novel, as it were. And these two positions both have a lot going for them and both have serious problems. And that intrigued me. And at the same time, the applicability of mathematics has always puzzled me. That you can, coming particularly from pure mathematics, as I had done very little applied mathematics, and found it was just so surprising that the stuff that I had been learning in mathematics classroom and developed by mathematicians by purely a priori methods, sitting down in their offices thinking, turns out to be exactly what you need to do almost any science.
Yeah.
And that also kind of intrigued me. And again, the answers to that problem didn't seem to lie in the mathematics department, but they don't lie in the philosophy department either. That's the appropriate place to think about it, at least, it seems.
That's great. That's so good. So I wanted to get into, I love those questions, by the way. Those are really good questions to be thinking through. And they've been plaguing me for a while too, which is fun. What I wanted to ask about, what is the philosophy of mathematics, and then maybe the difference between philosophical mathematics and mathematical philosophy. Is there a difference? Is it the same thing here? Or are we just splitting hairs?
So I think of philosophy of mathematics is about the philosophical study of mathematics. So just like, say, philosophy of biology is about the philosophical issues that arise once one is studying biology. Questions about how you classify organisms, what is a species, what's diversity. These are sort of questions that arise when you're doing biology. And there's nothing in a way that's distinctive that's just philosophy. It's an interesting collaboration between biologists and philosophers, but there are certain questions that you find in philosophy of biology that lean more on the philosophy side than on the biology side. But in order to do the philosophy of biology, you need to be a good philosopher, but you also need to know the relevant biology. You can't just sit in your philosophical armchair and say, oh, biologists should do this, that, or the other. Yeah. So that's how I sort of think about the relationship between philosophy and various sciences when you're doing philosophy of X for some X where X is a science. And so philosophy of mathematics, I think of as the philosophical questions that arise from doing mathematics, questions like what is a proof, what's the appropriate logic, what's the nature of mathematics, what's it about, does that affect the logic? For instance, if you're a fictionalist about mathematics, you think it's a work of fiction, then should you be subscribing to a different kind of logic, to the logic that's actually being used, and so on and so forth. These are all questions that, again, are not exclusively the purview of philosophers. Mathematicians think about these things as well, and it's ideally a collaborative effort. Whereas mathematical philosophy, I think of as more using mathematical methods to solve philosophical problems. So think of cases where you're using various kinds of mathematical methods, say from decision theory or game theory, to solve cooperation problems, to understand how language arises, how people can agree upon meanings of words. So in philosophy of language, there are these game theoretic models. They're using mathematical methods to solve philosophical problems about language, for instance. Or you might use, decision theory, again, mathematical methods to come to understand problems in various areas in philosophy. Pascal's wager, which no doubt your background would know very well.
Sure.
That renders very well to a kind of decision theoretic formulation. And then you can get very clear about what the assumptions that Pascal was making and so on and so forth. So I think of mathematical philosophy as using mathematical methods in service of philosophy. Whereas philosophy of something or other, like philosophy of mathematics, I think of sort of the direction is a little bit the other way. It's using philosophical methods to help us understand something about the nature of mathematics.
Okay. Now, you talked about decision theory and like if someone's doing hardcore like Bayesian reasoning and stuff like that, would that count as mathematical philosophy? If someone's doing hardcore Bayesianism?
Oh yeah, I mean, people no doubt disagree about this kind of usage.
Okay.
I mean, it's just labels for things, but that's what I would think of as mathematical philosophy.
Okay.
Sometimes in an area in epistemology, people talk about formal epistemology.
Yeah.
And formal epistemology, I think of as part of mathematical philosophy. It's using these formal methods, not always mathematical, sometimes, logical, using modal logics, epistemic logics like in the service of helping us understand what knowledge is. For instance, I think of that as, part of this formal mathematical approach to philosophy.
Okay.
Which is not to say that that's something you sign up for and that's all you should do, or that's all philosophy is. I just think it's an interesting tool one has in one's toolkit. And if your background is sort of more towards the mathematics and logic, the old saying, if the hammer's the only tool you have, the whole world looks like a nail. Well, that's me a little bit.
Yeah. That's great. So we got mathematical logic and philosophy of mathematics kind of in view here, and that kind of sets us up nicely to talk about Gödel and logicism. Real quick, let's go on logicism first, because I really like this idea of reducing mathematics to logic, and then I found out that it's kind of might not work. Can you give us what is logicism, and then can you explain whether you think it works or not?
So logicism is the view that mathematics is just logic in some sense or other, to be spelled out, and the details needn't concern us here. But the idea is that, we have a good grip on what logic is. And if mathematics were just logic, we would kind of reduce, two mysteries to one or something like that. And so the idea is that mathematical knowledge just is logical knowledge. You can formulate it in logic and you can just do it all with logic. And it's always dangerous to say that I think that program didn't work, because whenever you say that about any program in philosophy, there'll be someone who still thinks that it can work and will push through with it. But it's very, very popular in the early part of the 20th century. But I think it's fair to say very few subscribers these days. In part because you might think that mathematics carries with it a commitment to mathematical objects, at least on the face of it, right? So mathematics is full of statements like there exists a function such that, or the empty set exists, or there is an infinite set. These sorts of claims don't look like they're part of logic. And so if you could reduce that to logic, you would get rid of that ontological commitments, the commitment to these weird, spooky mathematical entities.
Yeah.
But I think it's fair to say it's generally thought that it didn't work.
Okay. Yeah, that's good. So that was that's like the famous proponents would be like Russell and Whitehead. Is that fair?
Yeah, and Frege.
Okay.
Starting with Frege.
Okay. Yeah, I like some Frege in my life. Okay. Well, so moving on from logicism to Gödel's incompleteness, and I've been looking to talk to someone about this for a while. I read up about it, and it was still tricky for me. But how would you classify Gödel? Is he a philosopher? Is he a logician? Is he a mathematical philosopher, a philosophical mathematician?
All of the above.
Okay.
I think. He's primarily, I guess you'd think of him as a logician, but he did serious, mathematical work in logic. His philosophical reflections on logic and mathematics were, work of a great philosopher. So it's like always when you've got a major figure, every discipline wants to claim them. So if you ask mathematicians, he would be a mathematician. You ask philosophers, he's a philosopher. So, but I think all of the above is the right answer.
Okay, yeah, that makes sense. Well, he's got these two incompleteness theorems, which a lot of people say were just this huge moment in the 20th century. Can you help us make sense of them? Like, maybe which one should we even start with, the first or second?
First, I think the second follows naturally from the first. So the first incompleteness theorem simply tells us that if you formulate mathematics in you've got a language that's rich enough to formulate basic arithmetic is all you require. And if you do that, then and the system is in fact consistent, that's important. That's often left out in people's sort of gloss on it. That if the system is consistent, then there will be some sentence of that system that can't be proven by the system. So there's a blind spot, as it were, in the system. And moreover, the blind spot is something that you can see yourself and recognize it as true. That's that's the kicker, as it were. So the sentence in question, sort of, easiest to formulate Gödel, so-called Gödel sentence, says of itself that it's not provable. Right, so you can formulate statements like that in this language. So this sentence effectively says, I am not provable. And clearly that's true because it's not provable. So it's true. So you've got this true sentence of the system that's not provable. So the system can't see this, as it were. It's a kind of blind spot in the system. And from that, but that's on the assumption that the system is consistent. It turns out from that, it's not too difficult to prove from the first incompleteness theorem. That's, that there remains there's a Gödel sentence of any such system, that one of the things that the system can't do is prove its own consistency. If in fact it is consistent. Again, that's the important clause there. So if the system's consistent, it can't prove its own consistency. So there was this great hope that you could formalize mathematics in some sense and then prove that it's consistent, given that there were these major events at the beginning of the 20th century when set theory was discovered to be inconsistent. So Russell's paradox and a bunch of other paradoxes arose around the same time. And they showed that set theory was inconsistent. And so set theory had to be reformulated. We now have the modern versions. We have several different set theories, but in fact, the sort of the generally accepted set theory, Zermelo-Frankel with choice. We would wish that it were consistent, but you can't prove that in the system. That's one of the results of that's Gödel's second incompleteness theorem, that you can't prove. You can hope that it's consistent. You can think that it's consistent on inductive evidence, like the problems that arose for naive set theory don't seem to be, you can't formulate those problems in ZFC. So none of the known paradoxes give rise to inconsistencies in the modern set theory. But that's not a proof that it's consistent. That's just like there are no known problems, right?
There could be one down the line, yeah.
That's right. If someone says, I can prove that my computer program is bug-free because I haven't found any bugs so far,
right,
that's not a proof that it's bug-free, right? So that's and moreover, what you'd think is you'd like to be able to prove that, we're talking about mathematics here where, proof is by far, the thing we're always looking for, a proof of this, not just a guess or a hunch.
Yeah.
And Gödel's second incompleteness theorem tells us that if the system's consistent, you can't prove its own consistency. Ironically, you can if it's inconsistent. If it's inconsistent, you can prove that it's consistent. But so some people take this as a kind of limitation of what you can do with mathematics. And indeed, that seems right. But you might think of it in these terms. There's a trade-off between consistency and completeness. You can get the completeness if you allow inconsistent mathematics.
Yeah.
And that's a road less traveled. But that's really what the theorem is telling you. If you think of consistency as non-negotiable, then you can't have completeness. But if you take it the other way around, interesting though, less traveled roads open up.
Yeah. So in logic, if you're a classical logician, many would say that there's this principle of explosion, that anything follows from a contradiction. But in a mathematical system, you can have inconsistency without explosion, because then it's what it seems like. You you can have a complete system. And I would think if it's inconsistent, they would just explode.
It depends on the underlying logic. So
Okay.
the still an interesting question about what is the underlying logic of standard mathematics. Most people say it's classical, but if you just look at the practice, it's not so clear that it's classical. So, for instance, when the contradictions arose, no one thought that proving from, for instance, the Russell paradox, which you formulate this set, the Russell set, and it's both a member of itself and it's not a member of itself. It's contradiction. And from that, you can prove anything, right? If you're using classical logic.
Yeah.
But the mere fact that mathematicians didn't do that is either a sign that they're not classical, or there's some kind of pragmatic considerations that come in on top of the logic, right? It's not unclear what's going on, but certainly no one said, oh, given the Russell set, I can prove Fermat's last theorem in 5 lines. We didn't have to wait for, the Wiles 100-page proof later on. Right? We can do that in 5 lines right now. That would either be seen as not a logical consequence, in which case it's not classical logic they're using, or it is a logical consequence, but it's somehow or other inappropriate to do that, which is some sort of pragmatic consideration. It's not clear why, but if you're absolutely right, if you're using classical logic and you've got inconsistent mathematics, you've got trivialism. Everything can be proven. So you don't want that. So if you're going to investigate inconsistent systems, such as naive set theory, for instance, then you need a paraconsistent logic, is the bit of term of art for those sorts of logics, that they're just simply logics that will allow a contradiction without anything following from them.
Okay.
Sorry,
Yeah.
that's right. It's not the case that every sentence follows from a contradiction.
Yeah.
There'll be at least one sentence that does not follow from a contradiction. That's all you require for a paraconsistent logic.
Okay. This is good. I think it was maybe Rebecca Goldstein. She had a book on Gödel, and she talked about how the Gödel sentence is kind of like a similar type of reasoning to the liar paradox. Are you familiar with that? Have you heard that before? Has anyone else made that comparison between a Gödel sentence and the liar paradox?
Yeah. I mean, it's the sometimes called diagonalization. It's a kind of trick where you in a nutshell, it's the kind of self-reference, like the liar sentence says of itself that I am false.
Yeah.
Right. And that leads to contradiction. The Gödel sentence says of itself, I am not provable. It's the same kind of construction.
Okay.
And clearly Gödel was thinking about the liar sentence and similar paradoxes, and realized that this was not actually, didn't give rise to a paradox here, but gave rise to actually a really serious limitation of mathematics. So that's the difference in the end. The liar paradox just is paradoxical. It gives rise to a contradiction. Gödel sentence doesn't give rise to a contradiction. Rather, it gives rise to an interesting and not anticipated limitation of formal systems.
It's so awesome. Yeah. And I love that. That's so cool. Um, from what I've read, it seems like the Gödel sentence, Gödel's incompleteness theorems, kind of crashed David Hilbert's formalism. Does that sound right? Did he ruin formalism for Hilbert?
Well, the details of the Hilbert program, yes. I mean, again, formalism is not a particularly popular view these days, although there are, again, caveat here, there are formalists around, and there's really interesting work going on. I don't, not suggesting that these people are crazy or like, they're doing really interesting work on formalism and trying to get something to work. And it's not that they don't know about Gödel's incompleteness theorems. Of course they do. And they're trying to work around it. But the details of Hilbert's program required, in effect, he required a finite proof of the consistency of mathematics. So he allowed infinite mathematics in his system, but he thought of mathematics as divided in two parts. There's sort of the finite part and there's the infinite part. And the infinite part is acceptable if you can prove that the thing is consistent via finite methods. So he required a consistency proof, but also with one hand behind his back, right? He had to prove it via finite methods. What Gödel's incompleteness theorem says, you can't have it no matter how you do it. Within the system at least, you can't prove the system's consistency by finite or otherwise methods.
Yeah.
So that particular approach, the Hilbert approach to formalism, the details of that system, that approach, I think it's fair to say that doesn't work in light of Gödel's results. People who would think of themselves as kind of Hilbert followers are trying to do stuff working around that. So it's not, I wouldn't say it's dead, but it certainly put a big dent in the Hilbert approach, at least.
Okay. Why might someone go in for formalism? I think I've read somewhere that it's like a advanced view on like the rules of chess. Like we invented this game of chess, but it's similar thing for mathematics. That it's like it's a maybe social construction, and just up a little bit higher. Why would I don't want to be rude to anyone's like psychology or anything. I'm just curious. Like why do you think someone would be interested in formalism?
Well, it has a lot going for it. I think it's spelled out in the right way. It's a very attractive view. I can understand, firstly, it's sort of worth pointing out that David Hilbert is one of the greatest mathematicians who ever have
Big
lived.
time. Right.
He's no fool. And he really thought that this was important to mathematics, to put it on a firm foundational basis. So he understood what mathematics was about. And he thought that formalism was the best shot at this. And not only was he a great mathematician, he's a very, very astute philosopher. I mean, probably no one would call him that, but if you look at his work, he was philosophically engaged with this problem about what is mathematics. Let's put it on a firm foundation so we don't get those catastrophes of finding set theory inconsistent and the like again. Let's get it sort of sorted out. Let's get the foundation sorted. So he saw formalism as the best approach, and there is a lot going for it. I mean, the idea is that mathematics is largely about proof, working out what follows from what.
Yeah.
And so it's not so much about mathematical objects as such, which are, as I said, they're kind of spooky and hard to understand how you can have access to them. How could you have knowledge of these things that don't have space-time locations? And, maybe we could talk about that a bit later on. But the problem of mathematical objects is a serious problem for anyone who thinks that mathematics is about these objects. Hilbert thought that, well, if it's about what follows from what, it's just about the formal formal consequences of particular axioms, for instance, then it's kind of like the rules of chess, right? No one says, oh, there's this big problem in chess. What is a rook? No, a rook is just the damn thing that plays the role of the rook in the game and is defined by the rules of the game. That's all there is to it.
Yeah.
You can have a wooden piece that counts as the rook. You can have a piece of paper with rook written on it. Or people play mental chess where there's no actual object. It's just sort of a mental construction, right?
Yeah.
And that's what follows from what moves are legal and what moves are not allowed, and what arrangements of the pieces on the board are possible given so many moves. So all these are interesting questions in chess, but there's no one gets puzzled about what chess is about. It's just a bunch of rules and what follows from those rules. Yeah. Turns out it's a really interesting and rich game. You could have other rules that lead to, much less interesting games like, snakes and ladders or something like that. But chess gives rise to a really interesting game. And so thinking of mathematics in those terms, it's a really rich and interesting set of rules that gives rise to this fascinating, rich area, but it's ultimately the study of what follows from what. It's this formal rules about, if I have a symbol like this, I'm allowed to replace it with something like that.
Yeah.
Right. And it also pays great respect to the notation, which is one of the things I think is really attractive about formalism. Mathematical notation is really, really quite important. Mathematicians have heated arguments about the best notation for this or that. And formalism tends to, one way of thinking of formalism is mathematics is really not much more than just a notation, right? It's really about this notation, what you're allowed to write after you've written something like that and you've got an equal sign, what are you allowed to write on the other side? So it's really highly focused on these formal implications and on the notation. And I think a lot of philosophy of mathematics ignores notation for things that arose by any other name kind of thing. It doesn't really much matter what you call it or how you write it. Whereas formalism actually played a lot of respect to the notation. And for what it's worth, that's one of the attractive features for me. I think, I'm not a formalist, but it got that bit of philosophy of mathematics right.
Okay, that's really interesting. I love finding those kind of things, the disparity or discrepancy between the actual thing and the philosophy of that thing. Like, like in philosophy of biology or something, or philosophy of science, the philosophers of science usually look for laws, and some of the scientists were saying, well, we don't care as much about laws. We're looking at models. So it's interesting to find that same kind of similar phenomena in mathematics. So talking about notation, and the philosophers of mathematics haven't paid as much attention. I love that. I think that's really cool because I think we need to do some more. Like I love closing those gaps. I want to close those gaps. So
it's changing. I think the philosophers of mathematics are now paying a bit more attention,
sure.
partly because of the work of James Robert Brown, who's written some terrific stuff on mathematical notation and has some wonderful examples of how results in mathematics sometimes just drop out of the notation in a way that really quite surprising. I mean, I learned a lot from thinking about some of James Robert Brown's examples, but he managed to convince me that notation is much more important than, and I was as guilty as anyone. I hadn't thought about notation very much at all. And so I give credit where it's due here.
Yeah, that's awesome. I love that. I'll have to check out some of his work. And yeah, this is really fun because now I have that in my head that notation is important, and I can mark that. And next time I talk to someone, hey, what do you know about notation? That's really fun. Are you familiar at all with Penrose's use of Gödel in the philosophy of mind?
Yeah, well, it starts with Lucas, right?
That's right.
So the
Yeah.
Lucas argument is that, in a nutshell, the Gödel sentence can't be proven by the system, but me, a human, can recognize that it's true. Indeed, I can kind of prove that it's true because I can run through the options, right? It says that it's not provable. So if it's what it says is the case, then indeed it's not provable. And if it's what it says is false, so you can run through this line of argument and convince yourself that it's, in fact, the Gödel sentence is true, but not provable. And so Lucas floated this idea that, well, there's something that a human can do that a formal system can't do.
Mm-hmm.
So for this idea that a human is just some sort of fancy computing device, right? Yeah. And this was back in the 60s, right? When computing was pretty primitive. I mean, most of our laptops are more powerful than most machines that people were playing around with. Yeah. And so it was a very early sort of thought about the mind just being some sort of machine. And it was thought that, okay, here's something that a human can do, properly trained human, not anyone recognizes the truth of the Gödel sentence, but it's not too hard. You can get, any undergraduate to see that it's true. Then here's something that a human can do that a machine can't. And so, in a slogan, the mind is not a machine, is the thought of Lucas. Penrose takes that a lot further with, adding stuff about quantum mechanics and so on and so forth. But the basic idea that arises from Gödel's theorem is that, there's some kind of difference between the human mind and a machine.
Yeah.
No, I think that's wrong. I think that's just straightforwardly wrong. But
that's what I was going for. Yeah, I wanted to get your opinion on that.
And not to say that the mind is a machine, but rather that line of argument for why it doesn't work, right?
Yeah.
So, for instance, it's very easy to get the Gödel sentence recognized. Just have another system that has that Gödel sentence added as an axiom. Right now it's provable because it's an axiom, right?
Okay.
But that system will have its own Gödel sentence, another Gödel sentence. So the theorem says for any system of a suitable kind that's consistent and is rich enough to formulate basic arithmetic, will have a Gödel sentence. Now, the fact that I can recognize the first Gödel sentence doesn't mean that I haven't got my own Gödel sentence.
Right. Yeah, I might have mine, but I can't recognize my own. I could recognize someone else's.
That's right. So there's nothing that says I can't recognize yours and you can't recognize mine. That's fine. What you can't do is recognize that prove your own Gödel sentence. So
that's the self-reference. That's the whole point of it.
Yeah. So the first problem with this line of thought, I mean, it's an interesting line of thought. I don't mean to condemn it. I think it's actually really kind of fascinating sort of thought to throw up when you sort of see the Gödel. It's very natural. When you first see Gödel's incompleteness theorem, you think, wow, all of mathematics, no matter what they do, they can't prove that. I can see it, I there's something special about me. It's a very natural kind of thought. But, what the theorem says is that the system cannot prove its own Gödel sentence. Now, nothing in Lucas or Penrose shows that you don't have your own Gödel sentence that you can't prove. That's the second thing to say is that it has to be formulated in a certain kind of way and it has to be consistent. Who ever thought that a human mind is consistent, right? I mean, that's a really strong requirement. I mean, just think about your own beliefs about stuff. You have kind of inconsistent beliefs, maybe compartmentalized. I believe some facts about geography of my own city, just roughly which streets run. This is an example of David Lewis's, I think. Roughly which streets run north, south, east, west when you're in that particular part of the city. And then another part of the city, you have other beliefs about which streets run northwest. And then in the overlap, you find because you're approximating, you've got inconsistent beliefs about the direction of a particular street. Right? That's very, very common to have those kinds of inconsistencies. And the fact that they're compartmentalized, neither here nor there, your overall belief systems are surely inconsistent. It'd be a miracle if we all had perfectly consistent beliefs, right? So again, the fact that you can recognize a Gödel sentence in another system from another system which is inconsistent. It's also about deductive systems. We work probabilistically as well. We have
sure.
I mean, so there are some differences between this kind of formal system and the human mind, but it's not, I think there are better explanations for it than there being something very special about the human mind.
Those are such good points. I got to chew on those some more. That I really, really like that. Especially the Gödel sentence, recognizing someone else's. That makes so much sense. And we're not consistent. Wow. Okay. I'm going to try not to get too hung up.
So you can, for instance, you can just build a series of systems. You have a system that can't prove, the system Gödel had in mind with the Gödel sentence, this sentence is not provable. Then just add that as an axiom to the next system. Now I can recognize that as its, as a theorem because, simple proof from axiom to theorem, you just promote it. But we'll have another Gödel sentence and add that to another system, and then you get another system that has another Gödel, and so you end up with this series of systems, each recognizing the Gödel sentence of the previous one, but not of its own. And now I'm not saying that is in fact what's going on with the fault in the Lucas argument, but it's not excluded. Lucas gives nothing to suggest that, okay, we've got our own Gödel sentences, and so we're just like the machine. We've got our own Gödel sentence. We don't know what it is, but just because we can see someone else's doesn't mean that we don't have our own.
Right.
So.
Well,
that's
I
just
believe
not excluded by the line of argument.
Right. I think that I believe that's Michael Glansberg's approach to holding on to classical logic in light of the liar paradox. And he says, well, we move out, and each time we consider it, we have to move out another level. But this is a similar type of thing. That's really fascinating. And he's dealing with the liar paradox, and we're dealing with this Gödel sentence, which has the same self-reference, which is really fun and crazy to think about. Man, that's so cool. Well, okay, so we've got logicism, we've got formalism. How about intuitionism? Can you help us think through what that is and maybe whether you like it or not?
Yeah, intuitionism is in some ways a really radical departure from standard mathematics. It was first proposed by one of the great mathematicians, L.E.J. Brouwer. And funnily enough, Brouwer, as one of his most famous results, a fixed point theorem, was not something he was entirely happy with. Celebrated theorem, really sort of cornerstone of a great deal of analysis, this fixed point theorem. But he used non-constructive methods to deliver this result. And what I mean by that is, in mathematics, you want to show that something exists, that there is a function that has some properties. One way to do it is to actually build the function and display it, right?
Okay.
Here is the thing. I can prove that there is, I can prove that there is an even prime number. 2, here it is. I present it to you, right?
Yeah.
And the other is to say, well, if there weren't, there'd be a problem. But I can't show you what it is. I can't show you the thing in question. I can just show you that suppose that there weren't an even prime number, then I, after a bit of work, show you that you get a contradiction.
It's kind of an indirect way of showing things, right?
Yeah. But you don't ever display the actual thing that you're talking about. You just show that there must be such a thing, right?
Yeah.
And that was the method that Brouwer used in this fixed point theorem. And he became really unhappy with that style of proof because he thought, I want to be able to see, I want to be able to construct the actual thing. And this led him to the view that those kinds of proofs are illegitimate in his view. And so what you needed to do was actually provide a constructive proof, by which he means construct the actual thing. If you're saying there is a function or there is a set or there is a group, whatever it is that you're talking about in mathematics, then if you're making some existence claim about it, you must be able to produce it. And showing that were there not such a thing, there would be a contradiction, that doesn't prove that it exists. That just proves that its non-existence is problematic, right?
Yeah.
And so he then set about trying to prove a bunch of results in mathematics and finding how far can you go with this program. And what you end up with is a different logic. So it's not classical. I mean, we talked earlier about what the actual logic of mathematics is in some sense an open question. But assuming that it was classical, this is a radical departure, because what you require is an intuitionistic logic, as it's called. And this means that some of these theorems of standard mathematics are no longer theorems. Some can be reconstructed, some can be proven by constructive methods. So you recover those. But famously, there are lots of results that you can't. You just cannot get via constructive methods. And so intuitionistic mathematics is, in this sense, a radical departure, because they actually disagree with mainstream mathematics, let's call it, on whether something is a theorem or not.
Okay, and they're just cool biting that bullet and saying, well, so much the worse for all we've taken to see, because you guys are using non-constructive methods and we have constructive methods.
Yeah, there'll be a lot of agreement. So there's a lot of agreement about stuff, but there will be some, cases where there is disagreement. And in fairness to the intuitionists, some of the disagreement cases are really puzzling results, right? So there's the famous Tarski-Barnach theorem, which allows you to, via non-constructive methods, the folk version of it is take a sphere, so consider an orange. You can decompose it into a finite number of parts and put them back together and have 2 oranges of the same size that you started with one. A way to feed the masses, if you like.
Yeah, seriously.
And so this result requires non-constructive methods. And it's sometimes called the Tarski-Barnach paradox, because clearly, if you pull an orange apart and put it back together, you can't have two oranges of the same size. The Tarski-Barnett theorem says that's actually a result. You can do that. The deconstruction is kind of tricky. It involves some non-measurable sets and some fancy stuff, but it's not as it's a finite decomposition of the original sphere, and you can't get that result in constructive mathematics. And constructive mathematicians say, "Yay!" Right?
Yeah.
We don't want that result.
Yeah.
And indeed, classical mathematicians have to begrudgingly accept this result because it's a theorem, but there's something deeply weird about the Tarski-Barnett theorem.
Okay. Yeah. So that's a plus for them. Okay. That's really good. Okay. That's good. This is all so fascinating to me. I'm having a hard time moving on from it, but I want to get to Wigner and his unreasonableness, the unreasonable effectiveness of mathematics. Um, I pulled this quote from your book, and I'd read Wigner maybe 2 years ago, his paper on this, but he says the miracle of the appropriateness of the language of mathematics for the formation of the laws of physics is a wonderful gift which we neither understand nor deserve. And I think elsewhere he calls it. Oh no, he's right there. Yeah, it's a miracle. It's miraculous. It's crazy. Um, what's Wigner really getting at? Why is it so miraculous? Why does he find it so miraculous?
I love that quote, by the way. He's a fantastic writer, Wigner.
Yeah.
So Wigner was a mathematical physicist. He was. I think the paper even starts out with this very interesting, folksy story where some friend who didn't know much about mathematics asks him what this symbol is, and it's the symbol pi for the ratio of the circumference to the diameter of a circle. And he says, "What's it doing there?" And it was, I can't remember the details of it now, but I think it was in a Gaussian distribution, and a normal distribution from statistics. And asks him what that symbol is, and Wigner says, "Oh, that's pi. That's the ratio of the circumference to the diameter of a circle." And he says, "What's it doing there?" And he said, "Oh, that's about the distribution of grades or something, normal distribution." And he says, "Oh, now you mathematicians, you just that's really you're making fun of me just because I don't know any mathematics now. You're just kind of you're just having a go at me. That how could the circumference of a circle, the ratio of the circumference to the diameter of the circle, have anything to do with student grades? I'm really insulted." And Wigner thought, "Oh, actually, I can see the point. I mean, what does the ratio of a circumference to the diameter of a circle have to do with distribution of student grades? It's amazing that these pieces of mathematics turn up in certain kinds of applications." And so we then got thinking about this. Like, there is a genuine puzzle here that various ways to formulate this, but the way I tend to think of the core of Wigner's puzzle is that mathematics proceeds by largely a priori methods.
Yeah.
So mathematicians sit in their offices thinking up clever axiomatic systems and then proving theorems from those systems. And then it turns out that those things that they've developed in the privacy of their own offices is exactly what physicists require to do general relativity and quantum mechanics, and biologists require to do evolutionary biology, and so on and so forth.
Yeah.
And once you sort of think about it like that, it's deeply weird that this a priori discipline, largely a priori. I mean, there are some empirical methods used in mathematics these days, but the bulk of mathematics is a priori, and that turns out to be exactly what you need to describe and understand the world. And so it's the problem of this applicability. Sure, if you're just developing mathematics for its own sake and you're driven by interest and elegance and mathematical beauty and all of these kinds of things, whatever they are, that's a whole other bunch of interesting philosophical questions.
Right.
But you're driven by some kind of aesthetic considerations in mathematics about what counts kind of interesting and beautiful mathematics, then that's what you need to do science as well. I mean, you could imagine it going the other way and thinking, okay, all that beautiful mathematics, fine, but it's just not applicable, right? The
Yeah.
world is a dirty, messy place, and you
Right.
need dirty, messy mathematics, and we need to get the mathematics that suits the physics, and so leave it to the physicists to work out the mathematics. And indeed, that happens a lot of the time. Not that I don't want to overstate Wigner's problem. It's not that physicists always go and knock on the door of a mathematician and there's the answer sitting on their desktop.
Yeah.
Very often it is this cooperation where the mathematics was developed in response to needs in physics or in biology or elsewhere. But that it happens often enough that the answers are already there on the shelf in the mathematics department. That's what I think is the core of the Wigner problem. How is it that pure mathematics turns out to be applicable as often as it does?
Yeah. Yeah, I love that. I love it's so fascinating. I want to ask you about different ways of thinking through Wigner's question. But I wonder just initially about like Zeno's paradox, and there's some ways of getting around it, or the tortoise and the hare, or Achilles. There's this problem of it seems like you can never motion's impossible because if you ever cross any distance of space, there's an infinite number of divisible spaces you have to first cross, and so it's like you have to cross this infinite. And some people just go, "Fine, you cross an actual infinite, whatever." Others say, well, no, that's because you're applying math in a way that is unreasonable. You shouldn't think of math as you shouldn't think of space as having like mathematical points in that matter or something. What do you make of that like counter claim that if we do apply math, we end up with Zeno's paradoxes like Zeno's?
It depends on which of the Zeno paradox, but I take it you're talking about the infinite divisibility, the one,
Yeah.
right? And there, I think actually mathematics solves that problem. I think
Oh wow.
I think that Zeno paradox is just arises by not having a full understanding of limits in calculus.
Okay.
So fair enough at the time of Zeno because there was no calculus then, but now I think that the solution to that paradox is just that. So the idea is for me to get from A to B, I must pass the halfway point of A between A and B, right? And for me to get there, I need to get to the halfway point and so on and so forth. And if space is infinitely divisible, then it looks like I need to make an infinite number of journeys in order to get from A to B. And an infinite number of journeys is impossible. That's the idea. But in fact, an infinite number of journeys is not impossible. Sorry, put it this way. An infinite number of journeys is impossible in a finite amount of time. That's the sort of thought that runs behind the paradox.
Yeah.
Right. But in fact, what we learn from calculus is that's just false.
Hmm.
Because the series of journeys take the first journey to be 1 unit. The second journey we're considering is half a unit and quarter and an eighth and a 16th and so forth. The sum of that series, half, eighth, 16th, so on, the sum of that series in modern calculus is 1. So indeed, doing all those infinite journeys gives you exactly the journey you wanted from A to B.
Yeah.
So you you've got to understand that. And then you asked the question, what's the amount of time it takes to do that, though? Well, the times for each of those journeys is take the first journey, the full journey, to be 1 unit of time. Half, so suppose you're traveling at constant speed, half, quarter, eighth, so on and so forth. So what you need to do is do the limits, do the relevant calculus here, and you get exactly the right answer. Okay. Now, again, without calculus in hand, that does look like a serious problem, but I think the mathematics actually solves that one. So
That's awesome.
I think that's a case
so good.
where, the applicability works out. Indeed, it was applications like that motivated calculus in the first place.
Okay.
Newton and Leibniz, when they're developing the calculus, weren't thinking about, as far as I know at least, weren't primarily focused on Zeno's paradoxes, but they were focused on problems in physics that had similar structure.
Okay.
How do you make sense of an instantaneous velocity? Right? With a velocity, you would think of it as being a displacement divided by a time. And if the displacement is zero and the time is zero, how do you make sense of an instantaneous velocity, right?
Yeah.
Looks like 0 over 0, that's undefined, you can't make sense of it. So, in many ways, calculus was developed in order to make sense of things like instantaneous velocities and the like. And that's precisely what you need to, solve Zeno's paradox as well, or at least that particular Zeno's paradox.
Okay. And would you say that we do cross an actual infinite then from getting to point A to point B?
I think there is a sense in which you undertake an infinite number of journeys.
Interesting. Okay.
But that's just by dividing it up. I mean, you can think of
Right.
it as each point, right? There is an infinite number of points between any two points. If space has the structure of the real numbers, that's an open question. But let's suppose, which is the supposition of Zeno's paradox, right?
Right.
We're actually presupposing that. You don't get the problem if you don't assume that to start
Yeah.
with. So assuming that, I'm allowed to use that as part of the solution as well, right?
Okay.
So if space has the structure of real numbers, that is that between any 2 points there is another point, and then you can kind of divide any interval up into an infinite number of sub-intervals, smaller. They can't just have each one with a minimum size, for instance. There'll be a finite number of those between any 2 points. But if you're allowed to divide them up Zeno-like, right, half, eighth, 16th, 32nd, and so on, then there are an infinite number of intervals there, and you traverse them all getting from A to B. So there is a sense in which you undertake an infinite number of journeys, but I don't see why that's problematic in itself. The thought, though, was to undertake an infinite number of journeys takes an infinite amount of time.
Right.
That's just false, because the journeys are getting smaller and smaller and smaller, so are the times. And so you can actually do that in finite time.
And they still add up to the same amount of time it would take to take the one journey. The large, yeah. That's
You have to spell out the details of what your velocity is and all the rest, but spelled out in the usual way, the time it takes to get from A to B is exactly the time that you would think that it takes from A to B, given the relevant velocity.
Yeah. That's really cool. And it's on the supposition that math does align with space in that way. But yeah, if it does, that's really cool to think that I'm going to go upstairs after this. I'm going to cross an actual infinite. That's kind of cool. It's cool that math is so applicable. I remember I had one math teacher who was very into math, and he was like, everything's math. And he just would go through stuff and how applicable math is to life, and how he's got 2 fingers, or he writes 2 on the board and then he erases it and says, did I just destroy the number 2? No, the numeral 2. And he absolutely blew my mind. And I think it's so cool. I think Wigner's onto something here with the unreasonable effectiveness of mathematics. What do you make of it? Like, in your book, you go over a couple different tactics for thinking through it. Some deny its effectiveness. Others just say, you get what you're looking for type stuff. What do you make of Wigner's contention here?
I mean, as I said, it was one of the things that got me into philosophy of mathematics in the first place. And it's one of those things where I feel like I'm no closer to understanding a solution than I was when I was an undergraduate student.
Sure.
And that's a good philosophical problem, I think, in a way, that you know a lot more about it. I've thought about different solutions, and I still think that there's something deeply puzzling. Some people are just not puzzled by it. They just think, no, Wigner was kind of confused or whatever. And I just don't buy that. I think that he really was onto something. Sometimes the way he formulates the problem suggested that he was buying into a particular kind of philosophy of mathematics. So I think he uses some anti-realist language.
Oh, right. Yeah.
So he says things like, mathematics was invented for such and such a purpose. And isn't it amazing that this invention, this kind of construction, it sounds like he's thinking that mathematics is a kind of work of fiction.
Yeah.
And then you find that this work of fiction turns out to be a documentary, right? That would be surprising, right?
Right. Right.
Tolkien writes these chronicles of Middle Earth, and it turns out, well, there actually is a Middle Earth, and it does, the maps at the at the front actually are accurate maps of Middle Earth, and it turns out he was writing a documentary all along. That would be deeply surprising, right? Mm-hmm. And so there's some evidence to suggest that Wigner was thinking along those lines, and if he was, then I think that does presuppose some controversial philosophy of mathematics to get the problem started. But I think the core of the problem is independent of what your philosophy of mathematics is, even if you're a realist, right? So mathematicians are not constructing works of fiction, but they're writing down actual truths about the mathematical realm. There's still a question of how that stuff helps physicists, right? Just because it's true doesn't mean that it's useful.
Right.
I mean, it's true that I'm, sitting here talking to you, but I'd be really surprised if that's the thing that's going to solve the grand unified theory of quantum mechanics and general relativity, right?
Yeah.
Just because it's true doesn't mean it's useful. So understanding why this particular bunch of truths turn out to be so useful, that's still something that even a Platonist, someone who thinks that mathematical objects actually exist and that mathematics is about true statements of that mathematical realm, even the realist, I think, has some explaining to do about how those particular truths turn out to be useful. Maybe the problem's deeper if you're a fictionalist about mathematics, and some evidence suggests that Wigner was sort of thinking in formalist terms. I mean, not unreasonably because of the influence of Hilbert.
Yeah. Okay. Yeah, that is a really good point. Yeah, and there's a fact of the matter, presumably, about the number of quarks or something in the universe. But who cares? Like that doesn't matter as much. There is a true fact, but but the fact that,
or even more trivial things, it might be that sort of above a certain number, then you can get a universe like this, and below some number, you couldn't get a life permitting universe or something like that. So maybe the number of quarks actually does matter in some sense.
Oh yeah, okay.
Not the actual number, but that there be enough of them to build
threshold.
the universe. But other things like just the number of incidents of the letter L in the Sydney phone book. If there are such printed versions of phone books anymore, I guess they're not. Yeah. But in the old days, that was a kind of classic example of something that was, there is a fact of the matter about, that, but absolutely useless for any purpose whatsoever, let alone, understanding physics. And yet mathematics, again, turns out to be important, not just for physics. I keep harping on about physics, but it's important for all, pretty much all of science. So solutions to this, for those to start with, for those who think that there's not such a problem, I'm inclined to say, well, there's a fair bit of cherry picking here. You're highlighting the success stories and ignoring the failures. And so, of course, it looks like mathematics is remarkably successful. Logician Chris Mortensen, I remember asking me a question when I was talking about this in a seminar once, and he said, "It sounds like it's." If I can rephrase Chris Mortensen's point, it sounds like you're making a statistical claim, right? It happens more often than not, or it happens enough for it to be surprising. And so, what you need to do is look at the proportion of successes to failures. The failures don't get published, right? They're the mathematical theories that led nowhere. And for the large part, they're in mathematicians' waste paper baskets. So in order to get this claim that there's something really surprising here, you need to go through the waste paper baskets of all the mathematicians in history and sort of see that there were more successes than failures, or there are enough successes for it to be surprising. So that seems to me as a reasonable kind of response. Although, even if it happens once,
right.
I still have this feeling. That's not an argument. That's just a fun feeling. Even if once a mathematician works out something a priori and it turns out that that's exactly what you need for physics, that's surprising enough for me. And surely it's happened more than once, right?
Right. I think, just the fact that it's a priori and in the armchair is fantastic. Like the a priori guys who keep hammering that, they have to go, not always, like you said, they don't always have to go to the mathematicians, but sometimes they do, and in a lot of major ways. It's just so cool, and it's so interesting to think that the a priori should match up with the a posteriori in that way, and that there's a human in between it with just this I don't know, 8 pound, whatever, 12 pound gray matter, and they're the ones seeing the connections and passing them along. It is really, really, really fascinating, and I appreciate the armchair way that mathematics goes about, because, like Timothy Williamson, uh, he says he bolsters philosophy because of mathematics. If you have a problem with armchair philosophizing, well, mathematics does a lot in the armchair, and so your precious theorems go out the window as well. So let's not go too hard on the a priori folks.
Yeah, I mean, there's certainly a place for a priori reasoning in philosophy. I'm not for a moment suggesting that there's a problem there. What I'm opposed to is earlier when I mentioned the armchair philosophizing, was armchair philosophizing about a particular area of science.
Right. That
So
needs to not be, that needs
yeah,
empirical data.
I think if you're going to be doing philosophy of biology, you need to look at what biologists are doing. You can't
Totally.
just say, I don't care what they're doing. What they should be doing is this, right?
Right.
That's the kind of armchair philosophy I'm personally opposed to, and I'm not sure that
Totally.
anyone, really does that. But same with mathematics.
Yeah.
You can get a long way in philosophy of mathematics without knowing very much mathematics. So some of the basic problems in mathematics, really things like, why is it that 2 + 2 = 4? What is that sentence about? And again, you open philosophy of mathematics textbooks and even research papers, you'll find 2 + 2 = 4 as an example a lot of the time, right?
Yeah. Yeah.
And it is because the problems start really, really early in basic arithmetic. But I also think that if you're a serious philosopher of mathematics, you do need to know a little bit more than basic arithmetic, because you can be misled. The methods of arithmetic might not be typical for the rest of mathematics. You need to know a little bit about what's going on elsewhere in mathematics.
Yeah.
As I said, a lot of the basic problems are easily statable, particularly for an undergraduate course. I mean, in my textbook, I try to focus on, at least early on, basic examples for people who, mathematics that everybody would have encountered. But I also try and stress that I think it's important to get grips with some of the higher mathematics, because apart from anything else, it's just cool and interesting.
That's right.
How can you not, how can you live your life and not know about the Tarski-Barnach theorem? It's an impoverished life, in my view.
That's right. That's right. Well, I really wish that I would have taken a philosophy of mathematics course before I got into math, because if I knew that there was all this cool stuff behind the scenes or undergirding, I think I would have paid more attention in my math classes, because now I'm trying to backtrack and learn myself, and not just for like GRE type stuff, but just because it's fun, just because it's interesting, and because I see kind of the foundational problems and questions. Uh, another I wanted to finish up by I got to ask you about realism. Um, I'm going to talk about indispensability probably, because that seems like the major argument there. But uh, do you have a particular take on this? Like, are you a nominalist, or maybe Aristotelian or a Platonist, or what do you think about like the foundation for mathematics or mathematical objects?
I'm personally, I'm a realist about mathematics,
Awesome. Okay.
Platonist. It's fair to say I think it's minority view these days. So I
Okay.
don't wish to speak for other philosophers of mathematics here. There's a genuine divide on these issues. The reason that I am a Platonist is because of the indispensability argument, which is
Cool.
due to Quine and, in some moods, Putnam. Putnam certainly wrote on this, but later distanced himself from the Platonist sort of conclusion, at least, of the argument. So the argument basically derives from the applications of mathematics. So it's not that the Wigner unreasonable effectiveness in a way tells you should be a realist, but it's another kind of more subtle approach to understanding the nature of the applications that leads to Platonism. So the argument basically goes like this. If you're a realist about anything, why are you a realist? Well, you're a realist because the things that you're a realist about are indispensable to understanding the world, put it very broad terms, and in particular for understanding, for a particular scientific area of discourse. So someone who's a realist about electrons is a realist because if you had particle physics without electrons, it wouldn't work, right? Electrons are indispensable to our best theory of subatomic particles, right? And they do some explanatory work. They explain why we have lightning, why we have electrical currents, why you and I are able to talk to one another at such distance right now. All of this would be absolutely inexplicable if we didn't have the theory of electrons. And the theory is committed to the existence of electrons. And so taking the science seriously, you're committed to the existence of electrons. So again, there are going to be people who are anti-realist about electrons. There are philosophers of science who say, no, it's only the observable parts that we are committed to, and the subatomic, unobservable stuff, that's the world behaves as if there were, or something like that. It's sort of they're a useful construction or a useful fiction to sort of fill in the details of what it is that we observe. Set those people aside for a moment. There are some people who do that, but for the realist who thinks that I'm a realist about electrons because they play an indispensable role in my best physics. Okay, so then you just push them a little bit further and say, well, mathematics also plays an indispensable role in your best physics. And by your own lights, you should believe in all and only those things that are indispensable to your best physics, say, or your best science more generally. Then you're committed to mathematics because mathematics plays such a role in your best science. Yeah. And what you find is a lot of people are happy with the conclusion that electrons are real, very unhappy with the conclusion that numbers are real.
Yeah.
And what they want to say is that there's some kind of difference in the way that they're used in theory. Electrons have causal powers. They play an explanatory role. Mathematics just plays some sort of representational role. And what you should have said in the first place is not that I'm realist about electrons because they're indispensable, but rather I'm committed to electrons because they're indispensable in the right kind of way. Now I've got to say something about what the right kind of way is. And I'm inclined to think that however you spell out that right kind of way, I can tell you a story that mathematics is indispensable in that same kind of way. So one way that people spell it out is electrons play this explanatory role, an indispensable explanatory role in our best science. That's why I believe in electrons. More recently, the debate over indispensability has focused on whether mathematics can be indispensable in this explanatory kind of way. Yeah. Can mathematics actually explain things about the physical world? And I, for one, think that it can, and that's a minority view again. Let me flag that.
Okay.
But another philosopher of mathematics, Alan Baker, also holds this view. So there are a couple of us who think that mathematics can play this explanatory role in science. So the reason for something happening in the world is because, to put it crudely, the mathematics made it that it had to be so. Not all explanations like that, but there is a breed of explanation, if you like, that is for this mathematical explanation. And if there is such a thing, that's a big problem for those who want to be realist about electrons, but anti-realist about mathematics, because it looks like mathematics is doing some explaining. And if you're committed to all the things that are indispensable for explanations in science, then mathematics is in there at the ground floor in a way. And that's my view. That's why I'm a realist about mathematics.
Okay. I really like that. It's intriguing. I wonder, does that mean you just need to change we need to change our view on abstract objects and say, well, looks like they are causally efficacious at some point, at least mathematical abstract objects?
No, I'm. You could do that, and there again, for every thought one has about philosophy, there will be some philosopher that holds that view,
Definitely.
and there have been those who think that mathematical objects are in fact causally efficacious. But that's not what I'm advocating here, at least. It's that rather that there are kinds of explanations that are non-causal.
Okay.
So there can be causal explanation is one kind of explanation. Why did the the red ball go into the corner pocket? Well, it was hit by the cue ball at such and such momentum, so on and so forth. That's a causal explanation.
Mm-hmm.
But sometimes their explanations are not causal, or at least the causal component of the explanation is not what you're interested in.
Like grounding or something, right?
I have less of a grip on what grounding is than I do on mathematical explanation, so I'd rather stick to mathematical
Okay.
explanation. So think of, for instance, the rings of Saturn. The rings of Saturn have these gaps. If you look at the rings of Saturn on a image, you'll see these black bands in the rings of Saturn. They're gaps where no particles, no dust particles or small pebbles, whatever, mostly dust particles, I think, ice particles, where there is nothing, right? That's what those black bands are. Very characteristic. They're kind of wide ones, narrow ones, all at fixed, distances from Saturn. And if you ask for the causal explanation for why those gaps are there, what you'll get is a history of every particle in the universe and why it ain't there, right? That's the
Yeah.
only causal explanation you could have, right?
Yeah.
Why aren't there any particles in one of the particular bands? Well, because all the particles are elsewhere, right? That's right. That's true. But it turns out that the explanation for why the gaps in the rings of Saturn are there are to do with harmonic resonances. And that's spelled out via the mathematics, spectral analysis.
Wow.
So the mathematics can actually predict exactly where those rings will be, the widths of them, and gives you the details of all of those gaps. So they kind of have to be there. Whereas if you're only in possession of the causal explanation, you can imagine saying, oh, well, it's just like a coincidence that nothing's there. So I'm going to set, a couple of particles, into one of the bands, the unstable bands, and you'll fail. And the mathematical explanation tells you that you will fail, but the causal explanation doesn't. Causal explanation makes it look like it's just a mere coincidence. Just like, why isn't there someone standing behind you right now? Well, there's just all the people in the universe, in the planet, are already accounted for, and none of them are standing behind you. Right? That's all there is to it. That is just a contingent explanation. There's nothing deep. I mean, I presume there's nothing, no reason why people would never want to stand behind you or whatever, right? It's just
Right.
a fact about no one standing behind you right now. Whereas the mathematical explanation tells you that just can't happen. It's an impossibility, or it's very, very low probability at least.
Yeah.
And so there's an example of a mathematical explanation that runs parallel with the causal explanation, but it gives you a lot more than the causal explanation. So I take it that the full story about the rings of Saturn is a non-causal mathematical explanation, or at least the mathematics is, as we sometimes put it, it's carrying it's carrying the explanatory load. It's doing heavy lifting here. Whereas the causal stuff, it's not that it's false. It is true that everything in the universe is elsewhere, but the mathematics tells you, and it had to be.
Yeah. Tells you why.
And that's, I think, what really explains it. You think, okay, now I understand why the rings of Saturn are as they are. It's because of the relevant mathematics here. And it doesn't really matter about the particular velocities and momentum of individual particles. All of that, initial conditions of the Big Bang, all of that stuff is kind of irrelevant. Given the configuration of Saturn with its moons, there have to be gaps in the rings of Saturn as they are.
Yeah.
So I take it that that's a mathematical explanation, and it's non-causal.
Yeah.
Right. It's not like the mathematics is bumping things around or pushing particles out of the way, or mathematics is just not the right kind of thing to do that. It just tells you something about what's possible and what's necessary and what's impossible and the like.
Yeah.
And a lot of the explanations have that kind of flavor. Such and such is the way that it is because it had to be that way. Or such and such is the way that it is because it couldn't have been any other way. So you often get mathematical explanations that have that kind of form.
Yeah. Man, you blew my mind going with Saturn there. That was so cool. So I wanted to finish up just by thinking through Benacerraf's dilemma, and this is nice because you're a Platonist yourself. I'm a Platonist too, so we can be friends here. I like that. But there's this problem for Platonism, and that's like if I I think for Benacerraf, he was saying if we want legit mathematics, then we're gonna have to be Platonists to say that we actually are studying real things, and that's seems like they're indispensable for our theories. But then we have this weird epistemology then where it's like, how can we, if we, evolved on this earth in a certain amount of time, how do we know about these non-spatial, non-temporal, causally inert or inept things? How is it that we know about them? Does that sound right? Is that maybe you can help me with the characterization of Benacerraf's dilemma?
No, that's exactly right, I think. So, I mean, the Benacerraf dilemma was actually twofold. The one was for the Platonists, there's this problematic epistemology. So if you believe in mathematical entities, they're not spatiotemporally located, they're non-causal, they're these abstract entities. How is it that you could have knowledge of such things? So even if they existed, let's put it that way, even if there were such things, how on earth would we know about them? Because all we can know about is stuff that we can causally interact with. And on the other side, the big problem for the nominalist, so in this same Benacerraf paper, this is why it's a dilemma. If you're a nominalist, you've got a problem. If you're a Platonist, you've got a problem. The nominalist problem was, how do you make sense of providing what you might think of as uniform semantics across mathematical and non-mathematical discourse?
Yeah.
So you want to say that Chicago is larger than Santa Barbara, right? In the appropriate sense of larger. Area or population doesn't much matter, right? Chicago is larger than Santa Barbara. And that's true because there is this thing called Chicago and there is this thing called Santa Barbara, and Chicago is bigger in the relevant sense than Santa Barbara, right? 7 is larger than 2, right? What you want to say, well, there is this thing called 7 and there is this thing called 2, and 7 is larger than 2 in the appropriate sense. You want to give exactly the same kind of story because the sentence has the same form. But a nominalist has got to say, there is no 7, and so either 7 is greater than 2 is false because there is no 7, or it's true for some different kind of reason, and I have to provide a completely different semantics for that sentence, just because it's about mathematics, even though I agree that it has exactly the same linguistic form as the Chicago-Santa Barbara sentence. I've got to pull it out and give it special treatment. So I can't provide a uniform semantics. Benacerraf says that's bad. You'd like to be able to have a semantics that worked on the structure of the sentences in question and didn't require you to have, special pleading for mathematical cases. So that's the problem for the nominalist, is providing this uniform semantics. The problem for the Platonist is about epistemology. How is it that we can have knowledge of abstract entities?
Yeah.
And Benacerraf formulated the problem in terms of causal theory of knowledge. So at the time, that was the dominant view, which is you have knowledge of something by coming into causal contact with either the state of affairs, the facts in question, or you come into causal contact with someone else who has come in causal contact. So you've got some sort of causal chain that leads you to the entities in question. Mathematics, that's just not possible because on the standard account of mathematics, it's about these abstract entities that don't have causal power, so you can't have causal contact with them. So first response is, well, the causal theory of knowledge is problematic, and became problematic, recognized as problematic not long after Benacerraf wrote his famous paper. But still the problem sort of persists. So, there's a thought that, well, while he talked about causal theory of knowledge, there's still a puzzle here. I mean, the way that the philosopher of mathematics, Hartree Field, puts it, the core of the problem is to explain the reliability of mathematicians' beliefs. If they have beliefs about this abstract realm, why is it that they're reliable?
Yeah.
So we can state the problem without relying on any particular causal theory of knowledge, just some sort of general reliability requirement here. And that is a puzzle. I mean, there are things one can say about it. I'm not sure I can say anything sensible in a couple of minutes, but it is a deep problem. I mean, it's something that I think every Platonist struggles with, trying to provide something that looks like a decent epistemology for their Platonism.
Yeah, I would imagine a pretty popular approach would be abductive, just inference to the best explanation. They make sense of our theories. So is that popular? Is that a popular method?
Yeah, I mean, my view is along those lines. I think the reason I'm a Platonist is because of the indispensability argument. So mathematics plays this indispensable role in our best scientific theories. And so every time you confirm a scientific theory, then you're confirming, if not the whole theory, large chunks of the theory. And so my mathematics is being confirmed along with the rest of the science because it's a package deal, right?
Yeah.
And so that's about confirmation of the mathematics, but that's small step perhaps from there to saying, okay, now I have some justification for the reliability of the mathematicans, or I have some reason to think that the mathematics that I'm signing up to that I have knowledge of that because I have knowledge of it in exactly the same way as I have knowledge of other abstract parts of science.
Yeah.
That there are gravitational waves, even when they're never detected. That we know that there are gravitational waves because the general relativity is confirmed, and gravitational waves are a consequence of general relativity. So we know that there are gravitational waves even if we don't detect them, I think. I mean, it'd be nice to detect them, but I think there is a sense in which you can say we have confidence that there are gravitational waves because they are a consequence of our best scientific theory about space and time. Mathematical entities are also playing such a role in our best theories of space and time, so I have confidence that I've got that right. What that leads to, though, and this is a kind of separate, kind of related problem, is you end up with this two-tier approach to mathematics. The bits of mathematics that get applied, you have solved the Benacerraf problem, arguably, for those bits, but not the rest.
Yeah.
So you end up with, the applicable bits of mathematics, having reason to believe in that. Maybe, just maybe, I haven't fully fleshed that out, but maybe you can spell out a solution to the Benacerraf problem in such terms. But it looks like it only goes so far as the mathematics that actually gets applied. And sadly, that's not all of mathematics.
Yeah.
So,
The Brouwer and the Intuitionists come through and say, well, show me, you have to show me.
yeah, so the higher reaches of set theory, for instance, that are applicable for other bits of set theory maybe, but it's not clear that physicists are ever going to need that or biologists are ever going to need that.
Yeah.
And so what you end up with is this uncomfortable kind of divide in mathematics between the applicable and the non-applicable. And you've got two different stories about that. And, again, putting my hand up here, that is a problem for people like me. I think you need to address that.
Okay. So I've told you a little bit about my background in theology. I wonder how ridiculous it would be if someone said, well, look, we have this Benacerraf problem. We have Wigner's, unreasonable effectiveness of mathematics. We got Platonism. It doesn't seem like a far jump to say, well, maybe an inference to the best explanation is that there's a God who designed the world. Mathematics, maybe we go in for divine conceptualism regarding mathematics. God designed the universe, and then designed us to think that way. Yeah. Does anyone try that? Is that maybe this doesn't have a lot of explanatory power when you get into the actual mathematics of it, but it's a higher level kind of question. What do you make of that?
Yeah, so one of the really major figure in philosophy of mathematics and philosophy generally, Mark Steiner, who sadly passed away a couple of years ago, one of the early casualties of COVID-19, sadly.
Oh, wow.
So Mark Steiner has this wonderful book on the applicability of mathematics, and he all but draws that conclusion that there's a kind of design argument in here. So he starts with the Wigner problem, trying to rehabilitate the Wigner problem, that philosophers had not really paid attention to it, and trying to really put it in modern terms in such a way that there really is this serious philosophical problem. And his work had big influence on me. I read Steiner's work on this and thought, he's absolutely right. I'm with him on this. All but the conclusion. He goes all the way to kind of, it looks like it's a big put-up job, right? It looks like the world was kind of designed in such a way to be a kind of mathematical world where mathematical, theories would be exactly the kind of things to actually, understand the world. And again, just speaking very loosely here, you can think of, imagine a world where mathematics was useless. The world was just too kind of crazy. Just shit was happening all over the place. No kind of coordination, and mathematics was just, it looks like the world was sort of, set in place to be a kind of mathematical realm. And there's one sort of small step from there to, well, there is this designer who was a master mathematician, right? Designed this mathematical realm. And Steiner all but sort of draws that conclusion. He's clearly heading in that direction, but leaves the conclusion kind of hanging a la kind of, Alfred Hitchcock, just a little bit of suspense at the end. But he clearly believed something along those lines, that the best explanation for why we have this applicability of mathematics and why the world itself is so mathematically sort of structured is that it was designed to be so.
Yeah, it's fascinating, man. This
I don't sign up to that, but
right.
But that's, I take it, the line of thought you're pushing, and you have a prominent philosopher on your side there in Mark Steiner.
Yeah, I'll have to check that out. It sounds really fascinating. We've covered so much, and yet so little of your actual book here. There's so much to it. It's an introduction to the philosophy of mathematics. So naturally, you cover a lot, but it's really helpful. Getting your feet wet, and yet it's not boring. It's not trivial. It's not trite. You still get in deep, but in a way that was really helpful. So I appreciate the book. Thank you for writing this. I think it's from back in 2011. Still awesome. Yeah. So mathematics is kind of timeless, and that's nice. So Dr. Colyvan, thanks so much for your time and for your book. If someone wanted to find out, read some more of your work or listen to more of your work, do you have a website or anything like that where people can find your stuff?
Yeah, I have a website. A lot of my papers are on a research page. If you just search for Colyvan, you'll find it. It's not too difficult.
Okay.
Yeah. So thank you, and thanks for your kind words about my book. It's nice to know that they're sort of doing some good out there.
Yeah, definitely. I'll put the link to your website in the description, so folks, you can find it there, wherever you're getting this podcast at. And again, the book is An Introduction to the Philosophy of Mathematics by Mark Colyvan, and it's one of the Cambridge introductions to philosophy. Definitely recommend it. Really great book. I obviously need to read more and bone up on my philosophy of mathematics, but this is a good start. So that's going to have to do it for now, folks. This has been Parker's Pensées, and as always, all glory to God.